So in this video, I'm going to be covering the node voltage and mesh current methods, which are two of the primary systematic ways of solving DC circuits, as well as other kinds. But in this video, I'm going to restrict it to circuits that have some combination of independent current source, independent voltage source, as well as a resistor network of some kind. Now, these two methods build on kind of three foundational principles. The first being probably the most well-recognized, which is Ohm's law, V equals IR, establishing the relationship between voltage, current, and resistance. And if you see it brought up in a physics context, you'll likely see it in this formulation. The second principle being Kirchhoff's current law, abbreviated as KCL, which essentially states that if you have a junction, which as an example this circuit would be this point here, this would be a junction, and basically states that if you have a junction and you have current coming in, it will be equal to the sum of the current coming out. Sum of the current going in is equal to the sum of the current going out. And this is important in the node voltage method, where we kind of use this to create a system of equations. Ultimately, that's what we're trying to achieve here is with these methods, is to get some form of system of equations that we can simplify and solve the circuit with. The last one being KVL, which stands for Kirchhoff's voltage law. Essentially states that if you have a closed loop, the sum of the voltages of each component will sum up to zero. This is an application of conservation of energy, I should say, and for KCL it was conservation of charge. But as an example, if we have some form of closed loop, such as this one, and we can assign polarities to each of these components, it essentially states that the sum of these voltages, when added together, will sum up to zero. The same thing with this loop, same thing with the outer loop, and so on. Now, if you have a circuit like this, where it's relatively simple and you can kind of simplify it, you see we have a series combination of resistors as well as a parallel combination and then maybe another series. You can kind of use Ohm's law and get all the information you need, but for more complex circuits you'll likely need to use one of these methods and get a system of equations, like I said, with these two guys. For this example, we'll start with the node voltage method. The first step here in a circuit is to assign your ground voltage, your ground node, which is quite arbitrary. You can do it at whichever node you like. It does not change the behavior of the circuit. You could do it at this node, or this bottom node. It does not change the behavior of the circuit. It merely changes where your reference of 0 volts is at. The voltage across each component will be the same, and the current going through each branch will be the same. Next, after that, you want to label all your distinct nodes. Again, to reiterate, a node is a place where two or more components are kind of joined together. It's an area where the electric potential is the same. So this whole bottom portion is a node. This part up here is a node. This is a node. And then this here is all the same node. Now, once you've identified them, you can label them. I'm going to just label them V1, V2, V3. Again, this is arbitrary. Just make sure you stay consistent. Now, here we're going to use Ohm's law and KCL to obtain our system of equations. So if we recall what Ohm's law is, V equals IR, we're going to use this formulation specifically to get our kind of currents. So for example, if we do KCL at node V2 up here, I'm going to use the convention of currents leaving the node. You can do them entering. It does not matter. You'll just get a different sign. But again, if we want to get our currents, remember that KCL states that all the currents entering a junction are equal to all the currents exiting. So here we can take that as being this current plus this current plus this current plus this current added together equals 0. It's all the same. So for the first one, the current going through this 3 ohm resistor, we'll use the voltage, which is V2 minus V1. That's the voltage across the resistor divided by its resistance, which is the first current. And then we'll do this second one going through the 8 ohm resistor, which will be V2 minus the reference, 0 volts, divided by the resistance. And next, the current going through this 15 ohm resistor, which will be V2 minus V3 divided by 15, and that's equal to 0. Not sure what's going on here. So this is one equation. We can also do it at node V3 up here. Now here we can see that we have an independent current source. Because of that, we'll be able to use it as one of our currents. So we can see if we're using the convention of all the currents exiting the junction, we'll have negative 5 amps leaving, plus the current through this 12 ohm, which will be V3 minus the reference divided by 12 ohms, plus the current going through the 15 ohm here, which will be V3 minus V2 over 15, and that's equal to 0. Again, this is all an application of KCL. Let's get rid of these real quick. So these are 2 equations. Now for V1, V1 is kind of a dummy node in a way, because we know the voltage of it. If we assigned, the way we set up the circuit, we assign this bottom node as 0 volts, and there's a voltage source here. So we know the potential difference across here is 16. So if this here is 0 volts, then this must be 16. So we can kind of assign it that way. So we can sub V1 in for 16, since we actually do know that. Okay, so we have 2 system of equations in terms of 2 variables here. Now we can just simplify. So once you've gotten your 2 equations, it's just algebraic simplification at that point. So here you can find the common multiple of all the denominator factors, which will get rid of these rational expressions and leave you with something like this. And you can simplify that further to your first equation. Likewise with the second one, multiply by the common factor, or the common multiple I should say. That will get rid of these guys, and you'll be left with a simplified equation. So you have your system of equation in 2 variables. You can solve this whichever way you'd like. You can use substitution of variables, elimination, or you can throw them into a matrix and get reduced row echelon form. But at any rate, you should be left with V2 being 15.25 volts and V3 being 40.11 volts. Now, once you've gotten these node voltages, you've essentially solved the circuit. You have all the information you need, and you can solve for the currents going through any of the components. So for example, if you want to solve for the current going through this 15 ohm resistor, it's not very good there, you can use Ohm's law. So you know the voltage of each of the terminals. So you'll be left with 40.11 volts minus 15.25 divided by the resistance of the resistor, which is 15, and you should be left with 1.657 amps. So here we'll be doing the same circuit, but this time using the mesh current method. The primary difference here is that we'll be using KVL to get our system of equations. We're going to be making distinct loops and writing KVL equations for each of them. So we're going to be finding unique meshes. Now meshes in a circuit are kind of like the smallest enclosed loop. So here we can see we have 3 distinct meshes we can note. And what we're going to do is we're going to assign a current variable for them. So for this first mesh we'll assign I1, likewise I2, and then I3. And next we're going to write a KVL equation. Now KVL says that the sum of the voltage drops in a closed loop is equal to 0. So for the first first mesh, we're going to sum up the voltage drops. So we can see we've defined I1 is going clockwise. So we'll have current entering here, so we'll be gaining 16 volts. And then since we're going this direction, we're going to assign polarities to each of these resistors. And the voltage drop across this 3 ohm resistor will be minus 3 times the current, which is I1. That's our variable. And here's where it gets tricky for some, where you'll have to realize that this is an intersection of meshes here. We have I1 defined in this direction and I2 going this direction. So you need to be careful to assign it. The voltage drop there will actually be the 8 ohms minus or times I1 minus I2, because I2 is going in the other direction that we defined. And again, this is all Ohm's law here. So this is we got the voltage from the voltage source, and then this is just V equals IR, giving us our voltage is here. And again, that will be 0 because of KVL. Likewise, we'll look at our second mesh here, I2, and since we're defining it going clockwise here, we'll define our polarities this way. And so we'll start with the 8 ohm resistor, so that'll be 8, again, because it's a shared mesh, it'll be negative 8 I2 minus I1, because I1 is going in the opposite direction this time of what we defined. And then this will just be 15 minus 15 times I2. And then finally, we'll have this mesh here. Now I3, kind of like the dummy voltage, so to speak, of the last example, since we have a independent current source here, we already know this is going to be 5 amps. And since we defined it as the opposite direction, we know I3 equals negative 5 amps. But that is kind of redundant. But here, since we know that, we know this will be 12 times I2 minus negative 5 amps, or I3, and that will equal to 0. And that's for the voltage across this 12 ohm resistor. So like the previous example, we've got 2 distinct equations in 2 variables. So again, once you simplify your 2 equations, you'll be able to solve for the mesh currents. So you should be left with I1 equaling 0.249 amps, or 249 milliamps, and I2 equaling negative 1.657 amps. And if you want to get the voltages we got in the last example, you can find those easily by using the bottom node as a reference node and multiplying the currents you found using your mesh method, and that'll give you your node voltages up there. But once you have the mesh currents, you've also solved the circuit, and you can get any other information you need from there.